So we're now essentially done with the slides going through the project Reactor operators, and we're going to wrap up with a few more case studies before we turn our attention to some new topics. So let's go ahead and take a look at the case study we're about to go through. This is part one of a two-part case study, and it's going to apply flux operators such as subscribe, flat map, and from array in order to create, multiply, and display big fraction objects asynchronously. And we'll also show how we can use some of the interesting mono operators like from callable, map, flat map, and subscribe on. We'll also demonstrate how you can take the subscriber class and implement it, actually subscriber interface, I should say, and implement that interface in order to be able to provide blocking subscriber semantics. There are, oddly enough, no blocking subscriber semantics that come out of the box with Project Reactor, unlike RxJava. And it sometimes is helpful to have these features, especially if you're writing test programs like we're doing here. So we're going to use the magic of inheritance and dynamic binding in order to create our own subscriber that can block. So you can find this particular example in the ex4 project in my reactive flux folder in my live lessons GitHub repository. So here we are in the ex4 project, and let's go ahead and take a quick look at what we're going to examine in the first part of this two-part lesson. So as you can see, we've got basically four asynchronous methods that we're going to be illustrating here in these two-part case study discussions. And the first one's going to take a look at a method called test fraction multiplications blocking subscriber, which, as the name implies, demonstrates how to do a blocking subscriber. And the second one's going to take a look at how we can basically combine the Java Streams framework with the Project Reactor framework and the Java Common Fork Join Pool. So as usual, we register a bunch of methods under test. We then run them all asynchronously using the async task barrier, and then we block the main thread waiting for them all to finish. So let's go take a look at these methods. Here's the first one, and I should point out a couple things here. We have a field in this test class called sRandom, which is a random number generator. You'll see how this gets used here in just a moment. Down here, we have the test fraction multiplications blocking subscriber method. We make a new string buffer in order to keep track of the information that we'll be using to display at the end of all the processing. We start out by saying what thread we're running in. We then create ourselves an array of big fractions with these values. You'll see that these are all legitimate values. We're not going to be generating any exceptions here by trying to divide by 0, for example. And then we're going to make an instance of our blocking subscriber class. And this class is actually defined here in the utils folder. We'll come back and look at that in a minute. And blocking subscriber acts very much like a normal subscriber in that you can provide it a number of lambda expressions or method references in order to be able to process different kinds of events. So for example, we have a method, a lambda expression that handles the normal processing of events when onNext completes successfully. And you can see in this case, it just goes ahead and appends the result we have here to the string buffer. And you can also see that when all the processing is done, we're going to display the results. Then down here, we have something that's going to handle asynchronous computations being finished. And you can see that we also have something that's going to keep track of whether or not we're going to be applying back pressure. And of course, in this particular case, we will not be applying back pressure at all. Okay, so let's go ahead and keep going. So that's our blocking subscriber. In fact, let's go take a look at blocking subscriber. It's worth examining that class. So here's blocking subscriber. The blocking subscriber class is a generic class. We parameterize it by the types of values that are being emitted by the publisher. And we then have the interface that we're implementing, the subscriber interface, which comes out of the box from Project Reactor. And here's the thing that's going to make this block. We define a local field called countdown latch. And a countdown latch is a very simple Java synchronizer, and it can be used in order to be able to allow the mechanism to wait until the value of the countdown latch reaches 0. And we're going to start it at 1, as you'll see in a second. So when it's not 0, then anybody who waits on the latch will inherently block. We then define a consumer to handle each on next value. We define a consumer to handle each error signal, which comes through on error. And then we finally have a consumer, which is really a runnable, not a sunnable, a runnable, to invoke on the complete signal. So these are basically the fields that we're going to use to store the Lambda expressions, which are called at the appropriate point. We also have this value that will indicate to the upstream publisher whether or not we're going to be doing back pressure. So here's the constructor. You can see what the constructor does. It's very straightforward. It just takes the various consumer or runnable or long values that are passed as parameters, stores them in the corresponding fields, and it also creates a countdown latch with the initial count of 1. You'll see how that gets used shortly. Here's the await method. This is what the subscriber is going to call after they make an instance of blocking subscriber and after they register the various callback that we just saw, the consumers and runnables and so on. And what it does is it just waits for the countdown latch in order to be able to become 0. And that'll just block. Here's the onSubscribe method. This is what gets called back automatically by the underlying Project Reactor framework when the blocking subscriber subscribes to the publisher. And what we're going to do is tell it whether or not to apply back pressure. We're passing in a value here, which you see here. If we look down here, you see when we create this particular, element, we're going to pass in a value of long max value, and that says don't use back pressure, just send the events as fast as you can. So here's the onNext method. You can see it just uses the registered consumer to accept the value, and that will go ahead and do whatever we told it to do. As you can see back over here, we basically said if all goes well, just go ahead and store the results in the string buffer. Over here on error, we go ahead and accept the error consumer to do whatever we want to do, which in our case turned out to be appending the error message and displaying the results. And then we release the latch because now we're done with the whole stream. And onComplete is much the same way. We run the completable runnable, and this is the hook method that gets run there. And we then go ahead and release the countdown latch as well. So that's what the blocking subscriber does. So let's go take a look and see how we use it. So after we register those various callbacks, then we use the from callable factor method on a mono to emit a large random big fraction. And then we're going to do something kind of fun. This is an interesting use of a feature available with mono. We haven't talked a lot about mono, but mono has some really cool operators as well. And you can see here what we do is we take this random big fraction, and then we're going to take the array of big fractions we created up here. So we have an array of big fractions. We have this other random big fraction. And what we're going to do is for each of the big fractions in the big fraction array, we're going to multiply their contents by the random big fraction. So this is, you can kind of think of this as like a for loop where we say for each element in the array, multiply the element in the array by this big fraction value we generated randomly. And we're going to use the flat map concurrency idiom in order to carry out that multiplication in parallel using the scheduler's parallel thread pool method. So here's what multiply fraction does. It goes ahead and multiplies the two big fractions together in the context of that particular scheduler. So that's our stream we have here. So we have this mono stream. And then we go ahead and we subscribe using the blocking subscriber. And so what's going to happen there is that all this processing is going to start running. And then the main thread of control is going to await for all the processing to finish. So this call here is going to block, waiting until we're done. When it's finished, it's going to return a mono to void. You can see we have a mono to void here. And that is an indication to the underlying async task barrier, which is the thing running over here in the main thread of control, that the computation in this particular test method is finished. So again, just to reiterate, we have a stream that emits a random big fraction. We take that and we multiply that concurrently in the background by the contents of the big fraction array. We use the blocking subscriber in order to do all the processing and handle the results. And then this thread of control, which is, again, going to be running in a background thread, just waits for all the computations to finish. So that's what is going to run in this particular example. So let's go back here and let's take a look at the next method, which is called test fraction multiplication streams. So this method is going to demonstrate how we can combine the Java Streams framework with the Project Reactor framework and the Java Common Fork Join framework. So let's see how that works. Once again, we start out by making a new string buffer, and then we make ourselves a stream of monos. We'll take a look at that in a second and see what the heck that's going to do. So we have a helper method called getMonoStream. And then we're going to collect those results into a mono list. And then we're going to go ahead and take the results and we're going to sort and print them using the trick we've talked about before, where we can do the sorting in parallel. Let's break this down and take a look at what's happening here. So here's the getMonoStream method. And you can see the monoStream method is going to return a Java stream, one of the modern Java features. This is not a Flux stream or an Rx Java stream. It's a stream. And here's what it does. It uses Java stream operations like generate to make a stream of random, large, and unreduced big fractions using the make big fraction method we've looked at many times before, that makes a very large numerator and a smaller denominator, and then creates a big fraction from a combination of those two values. We use the limit operation that says, hey, stop generating after we hit S max fraction number of random big fractions, so we don't go on forever. And then we're going to go ahead and use the Java stream. Oh, this is the Java Streams operation. And we use the Java Streams map method to go ahead and take the unreduced fraction that comes out of here. And then we're going to go ahead and reduce and multiply it using a scheduler that comes from the Java Streams family of schedulers. This is the Java Streams Common Fork Join pool. So we're going to use those methods. All those methods, as you can see, come from the Java Streams world. However, reduce and multiply fraction is quite interesting in that it will use mono operators to perform the reduction, do the flat map, and do this in the context of the scheduler we passed in, which of course in this case is going to be the version that's the Java Common Fork Join pool. So all this processing is done with the Project Reactor features. And what we do is we return a stream of Rx Java objects, but it's a Java 8 stream. So it's just demonstrating you can mix and match these two different mechanisms together in the same string. So what we have now is we have a stream, a Java 8 stream of monos. And then what we're going to do is we're going to collect it using something we call the mono collector. So we have a monos list collector. And let's take a look at monos list collector. So a monos list collector uses Java Streams features to make a collector that collects Project Reactor monos. Kind of an interesting idea. And here we're going to have the collector take a stream of monos. It's going to have the stream of monos stored locally in the so-called mutable result container as a list of monos, and then it's going to return a mono to a list of objects of type T, because the whole thing is parameterized by objects of type T. Here's what the monos list collector looks like in terms of the operations it defines. So it has a supplier that makes a new array list. That's what the mutable result container is going to be. It has an accumulator that adds the next mono in the stream to this array list. It has a combiner, which we don't use here because we're not using parallel streams, but if it was a parallel stream, it would add one list of monos to another. And then we have the finisher, and the finisher is the really interesting part. In the finisher, this is the part that's used to convert the mutable result container, which is this list of monos, into the final result, which is a mono to a list of objects of type T. And what we're doing here is we're going to use a very interesting method on the monos class called when. And when, as you can see, basically takes a list of monos. And what it's going to do is it's going to essentially materialize the results of that monos list when all the monos complete. So keep in mind what's going on here. If you think back to the actual processing, we had this stream of monos, and the stream of monos was reducing and multiplying big fractions in the common fork join pool. So that's all taking place in the background. And we take all those monos as they complete. And when they're all finished, then we get back a single mono that indicates that all the other asynchronous computations are done. Very powerful feature. And what we do in that case is we then go ahead and we take the original list of monos, turn it into a flux, and then we're going to call the block operation. And the block operation on this mono will actually not block, because we wouldn't have gotten this far had all those monos, we were using the when method to await the completion of, unless they're all done, we never get the materialized mono that indicates everything is finished. So this is really just used to convert the monos in order to be able to go from a mono to a type T, or in our case, a big fraction, and then get this back as a big fraction. And then the last thing we do here is we go ahead and we collect the results into a list. So we end up with a mono to a list of the objects. Very, very powerful idiom. And we've used this idiom in other contexts as well for Java streams and completable futures and so on. But now we're getting a chance to use this particular idiom in the context of our example that combines the capabilities of Project Reactor with Java streams. So we end up finally with a list of big fractions, and then we're going to go ahead and sort and print that list. And as you can see here, we use our classic trick of sorting it with quicksort, sorting it with heap sort in parallel, and then whichever one finishes first, we take those results and we display them. So that's basically a walkthrough of this example. I find this example is very powerful. It's a bit complicated, so it might be worthwhile going and running it. Speaking of which, I had started running this earlier, and let's see, it was running a different thing. So this takes a little while to run because it's doing a lot of computation in some of the later operations under test, methods under test. But you can see here that the blocking subscribe approach just goes ahead and creates those values and does the various operations on them. You can see the test fraction multiplication stream goes ahead and produces results that are printed in sorted order because we sorted it with either heap sort or with quick sort. So that's the end of this discussion. We'll come back and talk about the second case study here in just a second. This is one that illustrates some very interesting features in Project Reactor and shows how to combine this set of features with the streams capabilities that are also part of modern Java.